Welcome to The Explainer. Today, we're diving headfirst into the chaotic, dynamic, and honestly just super fascinating world of multiphase flow. More importantly, we're going to look at how human ingenuity uses some seriously elegant mathematical models to predict all this chaos on computers. Here's our roadmap for today. We'll start with the multiphase flow world, unpack the simulation challenge, and introduce the volume of fluid model. Then we're going to cover tracking the fluid interface and finish up with advanced multiphase modeling techniques.
All right, let's jump straight into Section 1, the multiphase flow world, defining the chaos.
So, at its core, multiphase flow is exactly what it sounds like. It's the simultaneous flow of materials with different states or phases. This could be a gas and a liquid and another liquid, or even a solid and a liquid. And multiphase flows are absolutely ubiquitous in our world. You see them in everyday weather like ocean spray, rain, fog, and mudslides. Over in the industrial world, they drive things like pollution control and papermaking. If you look even closer, it's the blood flow inside our very own bodies. Just think about the surprisingly complex bubble size distribution in a freshly poured Guinness. Yes, even pouring a pint of stout is a literal marvel of multi-scale physics. You can see how the density distribution dramatically shifts over just a 5-minute period. To truly understand and optimize everyday things like this, we absolutely need to be able to model them. Moving right along to Section 2, the Simulation Challenge, Predicting the Unseen.
Now, before we can actually simulate this stuff, we first have to classify the flow tautology. Generally, we divide these into two main categories. On one hand, we have dispersed flows. Think of our Guinness bubbles, where finite particles, drops, or bubbles are distributed within a continuous volume. On the other hand, we have separated flows. These are two or more continuous streams of different fluids that are separated by distinct measurable interfaces. Think of a wave rolling across the surface of the ocean.
But here's the massive challenge we're up against. It might be possible at some distant time in the future to code the exact motion of every single particle and chaotic fluid boundary into a computer. But calculating every microscopic interaction across a massive volume, it's computationally impossible right now. It would literally fry any modern computer. Because of that, simplifications are essential. We desperately need elegant mathematical models to bridge the gap.
Which brings us to Section 3, the volume of fluid model, the computational hero.
Enter the VOF model. It's a frankly brilliant technique designed specifically for immiscible fluids, meaning fluids that absolutely refuse to mix at a molecular level, like oil and water or air and water. Instead of trying to track every single molecule, the VOF model acts as a surface tracking technique on a fixed Eulerian mesh, which basically just means a stationary grid of cells. It uses a single set of momentum equations that are shared by the fluids to track mass and represent a sharp interface.
So how does it actually track that boundary? It does this using a volume fraction, represented by the Greek letter alpha. It's quite simple, really. If a computational cell has an alpha of 0, it means it is entirely filled with the secondary fluid. If it's 1, it's entirely the primary fluid. But if the value is a fraction, somewhere in between 0 and 1, it means the interface between the two fluids passes right through that exact computational cell.
Because of this highly adaptable volume-based approach, VOF is used everywhere across a massive array of industrial applications. Engineers use it to predict catastrophic dam breaks, model how jets of liquid disintegrate into atomized sprays, study sloshing inside massive fuel tanks, and even simulate wave structure interactions in marine engineering. It's pretty much an indispensable tool for seeing how fluids will behave before anything is physically built.
All right, Section 4, tracking the fluid interface, following the math.
VOF actually relies on a pretty fascinating 3-step process. Step 1 is representation, literally tracking the fraction of liquid in each cell. Step 2 is interface reconstruction. The system uses math gradients to figure out the angle, positioning a flat, planar interface inside that cell. And finally, Step 3 is interface movement. The interface evolves over time by solving fluid equations to move those fractions around based on velocity. So essentially, the computer is creating a piecewise linear approximation of a curve. Think of it like trying to draw a perfect circle using only straight lines. You're going to get this stair-step representation. The finer you make your computational mesh, meaning the smaller your grid of cells actually is, the smoother and more physically accurate that curve becomes. It is a really beautiful balance of geometry and physics.
Let's dive into Section 5, Advanced Multiphase Modeling Techniques, Optimizing the Solver.
Now, a major trade-off you'll face in VOF modeling is choosing between an explicit formulation and an implicit formulation.
An explicit scheme gives you incredibly sharp interfaces, which is amazing for accuracy. But it strictly limits your simulated time steps based on something called the Courant number, which is basically a computational speed limit you have to obey to maintain stability. Alternatively, you can use an implicit scheme. This has no speed limit, meaning you can compute larger time steps much faster, but it comes at the cost of less accuracy, slightly smearing the fluid interface due to numerical diffusion.
When you compare your options here, schemes like geometric reconstruction offer excellent interface sharpness, but they only work explicitly, meaning they come with a high computational cost. On the other hand, look at the compressive scheme. It's a great middle ground. It works for both explicit and implicit formulations, delivering good sharpness with a medium computational cost. And if you're just running a steady-state simulation where time isn't a factor at all, the modified HRIC scheme is fast, stable, and low cost.
Beyond just the grid itself, we also have to account for micro-level physics, like surface tension. If you've ever watched water beat up on a leaf, you know exactly how important surface tension is. In VOF, we can choose between models like the Continuum Surface Force, or CSF, which is a non-conservative approach that converts interface forces into volumetric forces. Or we can use Continuum Surface Stress, CSS, which is conservative and absolutely great if we need to model complex variations across the interface, like flows driven by temperature changes.
And what happens when these fluids actually touch the walls of a container or a pipe? Well, VOF can model wall adhesion and contact angles. This allows us to accurately simulate wettability effects, essentially dictating whether a solid boundary is hydrophilic, meaning it loves and absorbs the liquid, or hydrophobic, meaning it actively repels the liquid. Capturing this is essential for creating realistic meniscus shapes in your simulation.
Finally, there's this incredibly powerful hybrid trick for simulating things like fuel injectors, where a massive liquid spray violently breaks apart into microscopic droplets. Tracking every single tiny droplet with VOF would completely crash the system. So modern software uses the VOF to DPM transition. As droplets get too tiny for the VOF mesh to resolve efficiently, the software automatically converts them into discrete phase model particles. It seamlessly switches to tracking their behavior as points in space, maintaining physical accuracy without frying the computer.
So, we've zoomed from massive real-world ocean waves all the way down to digital fractions and discrete phase particles. Whether we're analyzing a beating human heart or a massive power plant, our world runs on multi-phase flow. Human ingenuity has given us the math to tame this chaos digitally. The only question left for you is, what invisible chaos will you simulate next?